What's that? Release the sequel. Yeah, I've got funding for a whole trilogy. Yeah, don't worry. Intensive contract negotiations. It looks like it's working.
I don't know why I cannot share the.
Looks like it's working. All right, let's rock and roll. So back for more Twistor theory. So now we're gonna, in the last lecture on this, we saw that there was a non-local holomorphic correspondence between complexified Minkowski space and this thing we called Twistor space, which was an open subset of CP3, where points in this complexified Minkowski space corresponded to these Twistor lines, these linearly holomorphically embedded Riemann spheres in the Twistor space, and points in the Twistor space corresponded to these totally null two-planes in complexified Minkowski space. And we also looked at one sort of application of this thing called the Penrose transform. We saw that we could solve these massless free field equations, these zero rest mass equations, in terms of cohomology. On Twistor space. And I think we even had time to give an example of this for momentum eigenstates, like a positive helicity graviton. Okay, so today I'm going to change gears a little bit and try to convince you that there's some natural relationship between Twistor theory and the Penrose transform and structures that we're familiar with from the conformal compactification of Minkowski space. Okay, so we've been hearing a lot about kind of quite robust mathematical formalism for dealing with asymptotically flat spacetimes in Simone's lecture, I'm going to be very pedestrian about this. So for me, an asymptotically flat spacetime is going to be one that admits an expansion in Bondi-Sachs coordinates, say at large future times. So asymptotically flat spacetime is one that admits a Bondi-Sachs expansion. So I'll be more specific about what that is. If those words don't mean anything to you, just stay tuned. What it really means is that there's some coordinate system U, R, Z, Z bar, such that large R corresponds to being very far away from regions of high curvature, and that you can conformally compactify the spacetime with a conformal factor that's basically like R. And then your future null conformal boundary has coordinates U, Z, and Z bar. Okay? Now, I don't want to sound like a broken record, but that's what I am. So what's the thing I always hate about Z and Z bar is that these are not global coordinates on the sphere, right? So these things, these are meant to be complex stereographic coordinates on S2. This U is retarded time, and R is a parameter a parameter along constant U hypersurfaces. Okay, so you know, an intuitive picture that I kind of grew up having of this coordinate system, which you may or may not find useful, is that you're kind of stacking up a bunch of light cones in your spacetime, and this is your coordinate system. So U labels the light cone, R takes you out the light cone, Z bar take you around it. Okay, and you just stack up all these light cones to cover the spacetime. But these break Lorentz invariants. Why? The same rant as ever about ZZ bar on S2, right? So we want to do things as Lorentz invariant as possible. So the question is there some version of these Bondi coordinates that isn't going to break Lorentz invariance, that in some sense will cover all of the S2 and allow us to talk about asymptotically flat spacetimes or the conformal compactification of Minkowski space without breaking manifest Lorentz invariance?
I'm sorry, can I ask a question?
Yeah, please.
You talked about Bondi-Sachs-like coordinates for the flat space, or you're talking about general?
At this point, I'm being very vague. Eventually, we're going to specialize to flat space, but the conversation we're going to have for the next 15 minutes is going to be generic asymptotically.
Because we have a general metric in Bondi-Sachs coordinates, of course, there are no coordinates.
No, indeed. Let me rephrase it then. Möbius invariance on the celestial sphere. SL2 invariance on the celestial sphere. Yeah, so whether you think of that as Lorentz invariance or not, you know, you'd still break that working with these coordinates. So what we're going to do is develop a kind of, okay, so before when we were talking about celestial holography or Twistor theory, we got around this problem just for the sphere by treating the sphere as one-dimensional complex projective space, the Riemann sphere, and replacing Z and Z bar with homogeneous coordinates on CP1. So the question is there some kind of homogeneous coordinate system, not just for z, z bar, but also for u and r? And the answer is yes, and this was, there's a kind of homogeneous Bondi coordinates developed by Sparling, Eastwood, and Todd. So, right, the choice of coordinate system should. So all I'm trying to do is set up a coordinate system that's going to manifest as much of the symmetries as possible at every stage in the calculation. Yes. So I'm not suggesting that calculations done in this coordinate system are wrong, just that there's a way to make them nice. And you may or may not be convinced of this at the end of this lecture. So okay, well, just again to keep hammering this dead horse even further. I mean, if you write things in affine coordinates on the sphere, in some sense you should always be able to convert back to homogeneous coordinates if you did things street legally. But sometimes this isn't like an obvious exercise. So anyway, so it turns out there's a homogeneous version of the Bondi coordinate system, which was developed by Sparling and written up by Eastwood and Todd in the 80s. If you kind of are a Twistor theory practitioner, you've probably heard this guy, George Sparling, is kind of one of the early superheroes of the subject, but one of these people who just never wrote papers. So most of his results are in papers written by other people who were unable to convince him to write them up. And this is one of the examples. So let's let lambda bar alpha dot be our standard holomorphic and anti-holomorphic homogeneous coordinates on CP1. For now, I know I've been in all the other lectures saying, oh, let's complexify our lives away, do everything in the kind of holomorphic category and not worry about signature. For now, for the next little bit, I'm going to really stick to Lorentzian real stuff. So let's think of lambda bar as really being the complex conjugate of lambda. So this is just the holomorphic and anti-holomorphic coordinate system, a homogeneous coordinate system on CP1. And of course, we can always recover these affine coordinates by going to a patch, right? So just to keep the same thing in mind, we can always go back to the stereographic coordinates on a patch, for instance, where lambda alpha is equal to 1 comma z. Okay? So that would be on the patch where lambda 0 is not equal to 0. These are two component.
No, the word next to
Standard, sorry, yeah. So standard is a relative term. It's standard for me, it doesn't mean it's standard for everybody. But yeah, so these are, what I mean by this is just, these are homogeneous coordinates on CP1. They're two complex numbers, we consider them up to scale. Okay. In the same way we've been doing in the previous lectures, okay? So now, what we're going to do is define the following homogeneous coordinates. U R lambda bar alpha dot, and they're homogeneous in the sense that we consider them up to the following rescalings. If B is any non-vanishing complex number, I consider this tuple of coordinates to be equivalent to this one if they differ. I consider any two tuples of these coordinates to be equivalent if they differ by this scaling. So this bit, this is fine. This is just the projective rescaling for homogeneous coordinates on CP1, right? But then I'm saying U, I identify it with this U if it differs by mod squared of the B, where B is the same B that I scaled my lambda and B bar by lambda bar, and R by 1 over mod squared of B. Okay? So you can use these to define some coordinates x alpha dot on your space-time as follows. You take x alpha dot is equal to u t alpha. I'll explain what I'm writing here in a moment. Okay, so these things carry this weight, this projective, well, it's not projective because these are not projective rescaling. This homogeneous weight in B. So I can't really think of them as space-time coordinates as such, but you can build your space-time coordinates out of these things by picking some constant time-like vector and considering this combination of things. So it's a nice exercise in understanding to make sure that these quantities don't carry any weight under these B scalings, right? So here U carries weight if you like 1, 1 in B bar, but I've divided by this lambda hat thing. Lambda hat is linearly related to lambda bar. So under one of these scalings, this lambda goes like B, this lambda hat goes like B bar. That cancels the scaling in U here, so this term's copacetic. Here, R goes like 1 over B bar, so that eats up the B that comes with lambda and the B bar that comes with lambda bar. Okay. And for
You mean that there are infinite amount, they're family parameterized by family of coordinates parameterized?
yeah, so exactly. So the reason why you need some choice of time-like vectors is because you want this U to be a retarded time. So it needs to kind of point in some time-like direction. You can make very simple choices of this T and the patch for lambda and lambda hat to go back to the Bondi coordinates you know and love. All right, so maybe that's a good exercise for us to go through. So first, let me just say that this makes it clear that R is like a parameter along outgoing null vectors lambda bar alpha dot tangent to constant U hypersurfaces. So that's exactly what we want for our Bondi coordinate system. And the choice of T this is basically defining a choice of conformal factor on the 2 sphere. Conformal factor is given by this lambda hat thing. And if I take, for example, let T alpha alpha dot just be the identity matrix, then it's a fun exercise in the 2-spinner formalism to work out what this conformal factor is. You just find in the patch corresponding to the stereographic coordinate z, this is just 1 plus mod z squared. So it's the round conformal factor on the sphere. But the point is, you don't, Bondi coordinates are completely fine for any choice of conformal factor on the sphere. It doesn't have to be the round one, and that choice is sort of being parameterized by choice of t. Well, 3. Well, yeah, okay, yeah. No, 4, yeah. So let's see. The choice of conformal factor is a choice of function on the sphere of appropriate spin and conformal weight. And I guess there's a certain number of spherical harmonics worth of those. The L equals 0 and L equal 1 ones. And there's 4 degrees of freedom there. Yeah. So, no worries. Right. Okay. So usually in the Bondi-Sachs formalism, the data of your asymptotically flat spacetime comes with kind of 2 numbers that label it. We usually call them spin and conformal weight. And usually in the Bondi-Sachs formalism, the way you define the spin and conformal weight is of a given quantity is you pick some null tetrad that you use to define your coordinate system, and then you consider rotations of that null tetrad, and then the way your quantity scales under those rotations is the thing that defines spin and conformal weight. Okay? One advantage of working with this formalism is that it makes the definitions of spin and conformal weight much more transparent. So let curly O PQ be, well, for all integer P and Q, be the bundles over your spacetime whose sections have the form of some functions of u, r, lambda, and lambda bar that transform in a certain way under this homogeneous rescaling. Right? So again, remember curly O yesterday in Twistor theory when it had 1 entry, it was telling us the sort of projective weight of a function or a section of a line bundle defined over a complex projective space. We're doing the same thing here. Now this curly O has 2 entries because we want to keep track of scaling in B and scaling in its complex conjugate B bar. Okay? So don't think too hard about this. This is just a symbol that means functions that transform like this. Of course, they're not really functions because they have this transformation property. They're sections of a line bundle. Okay? So spin weight S, this is now just the difference P minus Q over 2. Right? So a spin-weighted function is a section of one of these line bundles in this homogeneous coordinate system, and you read off the spin weight by just looking at the holomorphic scaling weight, looking at the anti-holomorphic scaling weight, and taking their difference and dividing by 2. Conformal weight is the other linearly independent quantity that you have, which is P plus Q over 2. Okay? So I don't know about you, we all have our preferences. To me, this is a much nicer way to keep track of things like spin and conformal weight than worrying about tetrad rotations. Okay? I just look at some quantity in my that's living in my spacetime, or some bit, some component of my asymptotically flat metric. I write it in this homogeneous coordinate system. I look how it scales, and that tells me what its spin and conformal weight are. Yes?
At this level, since we haven't imposed any representation of SL2C on these vectors, is there a reason for P and Q to be integers?
Yeah, because, okay, so I've said, oh, don't worry about it. This thing isn't a bundle. It doesn't define a line bundle if they're not integers. Yeah. So, okay, what it really defines is a sheaf, and this needs to obey some kind of co-cycle condition for the thing to be well defined. It won't be well defined as a sheaf if P and Q are not integers. Okay, so what does the Bondi-Sachs expansion of an asymptotically flat metric actually look like in these homogeneous coordinates? So this now looks like, we're going to write a line element. This line element, of course, has to be neutral under these homogeneous rescalings, right? So every term that I write here had better be a section of O0, comma 0, right? Or else it doesn't make sense. Okay. So what we get is 2 du dr minus r squared d lambda bar minus sigma 0 over r d lambda squared minus sigma bar 0 over r d lambda squared plus 1 over lambda hat squared minus 2 b over r du squared minus du. I'll explain my notation in a moment, I promise. Okay. So, okay, so what's going on here? So here, d lambda, this is the thing we introduced yesterday when we were talking about the Penrose transform. It's the weight to holomorphic one form on the sphere. D lambda bar, that's lambda bar, d lambda bar, square bracket. Okay. This funny looking thing, which is called et, this is the spin-weighted covariant derivative on the sphere. And if you crack open any of the old kind of GR papers, this thing, it's a differential operator. And you should basically think that it's sort of acting like d by d lambda, but when you write it in affine coordinates on the sphere, you have to, there's a bunch of factors, powers of the conformal factor on the sphere that appear inside and outside of the differential operator, and those powers depend on the spin weight of the thing that you're acting on. Okay? But one of the awesome things about working in this coordinate system, these homogeneous coordinates, is that this eth operator is dead simple. Okay? So what does it actually look like in these in these homogeneous coordinates. So here, eth, this is just lambda hat alpha over lambda hat d by d lambda alpha. Okay. Now you might say, wait a second, Tim, I thought this was supposed to be spin weighted. Why doesn't this have some s here, depending on the spin of the thing it's operating on? Well, that's the great thing about working in these homogeneous coordinates, because here I could come through with lambda contracted into some arbitrary reference spinner, use something called the Schouten identity, and this thing would be proportional to the Euler operator, the homogeneity operator on the sphere, and that will tell us the spin weight of the thing that it's acting on. So it does secretly know about the spin weight. The advantage of writing it in terms of these homogeneous coordinates is that you don't have to keep explicit track of the spin weight of the thing you're operating on anymore. It does that for you. Okay. So this thing, as a differential operator, if you like, it sends things that are in O, P, Q to things that are in O, P minus 2, Q. Why? Because it lowers the weight in lambda by 2. Sorry, that's 1. Okay. Et bar is just the complex conjugate of this dude, right? So it's acting like d by d right? And this thing sends sections of OP, comma Q, sections of O, P, Q minus, sorry, it is minus 2. Okay. This lowers the spin weight by 1, this raises the spin weight by 1. It's an unfortunate choice of conventions that I've made, because you might have naturally said this thing should be a spin raising and this one a spin lowering, but okay, we are where we are. Okay, then there's some other bits appearing in this expansion. This sigma naught thing, this MB, sigma naught bar. These are the familiar bits of data. Hopefully we've all met at some point in the Bondi-Sachs expansion. So sigma naught, this is a function of u, lambda and lambda bar, valued in curly O minus 3, 1. Sigma bar naught of u, lambda, lambda bar. This is in curly O 1 minus 3. And these things are the asymptotic shear. Right? This is the free radiative data of the asymptotically flat spacetime. This MB thing, which is also a function of u, lambda, and lambda bar of weight minus 3, minus 3. This is the Bondi mass aspect. This is the thing that generalizes the Schwarzschild mass, kind of Coulombic contribution to the metric, to generic asymptotically flat spacetimes. You shouldn't think of this as a piece of free data, though, because its U evolution is completely determined by the shear through the asymptotic Bianchi identities. Yes? Why do I call it shear? Because it is literally the asymptotic shear of a constant U hypersurface in the large R limit. So it has a literal geometric optic interpretation as the asymptotic shear. So remember, these constant U hypersurfaces are sort of like light cones or generalized light cones. What this sigma naught is controlling is the sort of transversal deformations of those light cones at large R. Well, I haven't said what null infinity is yet. Yes, if you conformal compactify, this is literally the shear of those constant U hypersurfaces at null infinity, future null infinity. They'll be vanishing. Right, okay, so we need to keep track of whether we're talking in the physical spacetime or the conformally scaled spacetime. So the shear of those constant U hypersurfaces falls off like 1 over r squared. But in the conformally rescaled metric, at scry, it's sigma naught. Right, so it's the same like with the Weyl tensor, right? The Weyl tensor falls off. With a metric like this assumes that the Weyl tensor peels. So the Weyl curvature goes to 0 asymptotically in the physical metric. But in the conformally rescaled metric, it goes to some functions on scry, on the conformal boundary. Sorry. So null infinity is a non-expanding horizon? Okay. Yeah, it may be that for that interpretation it's the case, but in a generic asymptotically flat spacetime it's not true. And one can cook up examples where it's not true, like a plane wave or something. Yeah.
Short question about notation. Everywhere here, bar is
bar is honest complex conjugate.
But except this sigma and sigma bar.
No. So for now, these are really the complex conjugates of each other. So complex conjugates flips the arguments in this OP-PQ because it turns a lambda into a lambda bar. Yeah, and that's good because there should only be 2 real degrees of freedom. Yeah, exactly. Yeah. So these are like I said, this complex function is encoding the kind of on-shell degrees of freedom of the radiative degrees of freedom of the metric. And the only freedom you have in this Bondi mass aspect are like, they're not constants of integration, but functions of integration on the sphere. The U dependence is completely determined by these guys. So you shouldn't really think of this as free data. Yes, this is real. And you see that it's real because -3 and -3 here, complex conjugation. So, I mean, this isn't enough to make it real, but for it to have a chance of being real, it has to be in an curly O, P, comma, P. Because otherwise, it can't be real. So yeah, this is consistent with reality of the Bondi mass aspect. Yep, okay. Okay, so now let's conformally compactify this metric. So we do this with a conformal factor that I'll call big R, which is just 1 over little r. And that leads to a conformally rescaled metric. So the hat means conformally rescaled here, which is like, so this is r squared ds squared. That's minus 2 du d big R minus d lambda bar plus r sigma naught d lambda squared plus sigma bar naught d lambda bar squared plus order big R squared terms. So it's the usual story. We reach the conformal boundary by sending the conformal factor to 0, or 1 over r to infinity. Right? So the the null conformal boundary is then d squared scribe plus. This is some 0 times du squared minus a conformal metric on this. Right? So we see the expected result. That scribe plus is like r plus s2, r cross s2. Okay. Now, so now, what we've recovered from this is a sort of homogeneous coordinate description of the null conformal boundary itself. So now, scry plus inherits these coordinates u, lambda, lambda bar, which we consider up to overall rescalings of this form. So these are just the kind of homogeneity relations we had for the whole spacetime, but now we just have u, lambda, and lambda bar left in the game. And that means that in this kind of homogeneous setup, scribe plus is the total space of a line bundle. Which we'll call curly O 1, 1 R over CP1. So what is this line bundle, right? Where sections of this thing I'm calling O 1, 1 R are real valued homogeneous functions on the sphere. Okay. F lambda bar such that if I do a projective rescaling on the sphere, I get mod squared b out in front. Okay. So why is scry the total space of this line bundle? Well, the base of the bundle is just CP1, so that's just our lambda and our lambda bar coordinates. And when we do a projective rescaling on the base, the fiber coordinate u scales like mod squared of b. So that's exactly what one of the sections of this line bundle does. And it's also real, right, because the Bondi time is real. So that's the sense in which, in this picture, scry is the total space of a line bundle. But total spaces of bundles are typically affine spaces, right? So total space of a line bundle over a sphere is affine, by which I mean there's no preferred choice of origin for u, right? So we have there's no preferred origin for u, the coordinate on the fibers of this line bundle. So we're free to shift u to u plus any section of this line bundle. what are these? These are super translations, right? So I think this is like a really nice way to see super translations popping out, because what they're basically emerging as the symmetries of this description of scry as the total space of a line bundle. Usually, if we do the usual thing of, thinking of scry as this, manifold with a kind of null metric on it, then diffeomorphisms which preserve that metric, you could have U dependence in this F, right? And instead, one usually has to go through some gymnastics about strong conformal structure to get rid of that U dependence. But here it's not an option, right? If I shifted this thing by some F that depended on U, then it wouldn't be a section of the line bundle, right? So it's not allowed. This is the difference between things called the Newman-Unti group and the BMS group. So somehow the Newman-Unti group just can't appear in this framework. Okay, it's not allowed. So, for instance, if I take my F lambda bar, remember this thing has to be weight 1 in lambda and weight 1 in lambda bar. So the easiest thing I could think of to write down here would just be some linear function in each of them, right? And those are just the translations, right? Poincare translations with, defined by that vector A. Okay. So the symmetry group that we recover for scry in this picture is these shifts of the origin, which we're allowed to do because it's an affine space, semi-direct product, Möbius transformations on the spherical base of the fibration, right? So that's semi-direct product, super translations with SL2, that's BMS. Right? Okay, so the asymptotic symmetry group that we've all been taught to expect when you have this Bondi-Sachs expansion just falls out in your lap in this way of doing things. Okay. So now, this discussion has been for a generic asymptotically flat spacetime. Now let's just consider flat spacetime. So we're going to consider now Minkowski space. Okay. And we want to ask a seemingly innocuous question, but which I think is a good candidate for one of the first examples of holography in the literature, so to speak. It's be a little bit after Bekenstein-Hawking, but I think is in some sense more close in spirit to the sort of thing we think about when we think about holography today. We want to know how do you reconstruct bulk Minkowski space from information at scry plus. Okay, yes? Where did I assume it? When I wrote down the Bondi-Sachs expansion. You could write Bondi-Sachs in de Sitter also, and the expansion would take a different form to the one I wrote. Yeah, and the conformal compactification formal factor would be different, and the resulting metric that you got on the boundary would be different. Does it answer your question?
Yeah, but also consider like the visitor also strike class from the R process.
Whoa.
I can just coordinate the visitor, but again, my strike class can be R process.
I mean, I would have said for, I don't want to offend anyone. I would have said any civilized conformal compactification of pure de Sitter should give S3 as scribe plus, but yeah. Yeah, so okay, the point here is that this coordinate system that we wrote here was adopted to kind of null congruences that were compatible with the asymptotically flat condition. This expansion would not work, and the homogeneous scalings I assigned everything wouldn't work because they're not compatible with the asymptotic symmetry group being the de Sitter group. So somehow the homogeneity scalings that we assigned everything here, it looked like I just guessed them, but they're sort of the only scalings you can give which are going to be compatible with Poincare symmetry, or sorry, Lorentz symmetry asymptotically. So in de Sitter you won't have this, so you couldn't use these coordinates. Sorry, does it answer your?
Yes.
You don't look convinced, but.
I see that you expansion will be different.
Yeah.
I still believe that in the figure you can on slide you can set up some coordinates which is again R process. But Q expansion is different.
Yeah, I think they can't be global though. If it, yeah. Yeah. Okay. So the whole point of these coordinates is that they're global. So, okay. I mean, I take your point, but yeah. Okay, so the question we're trying to ask is sort of a bit like what you might call bulk reconstruction nowadays. You're at the boundary. You want to understand how you can reconstruct your bulk spacetime from information that's just defined at that boundary. And this is a question that was first considered by Ted Newman back in the 70s, basically. So let's take any point, x alpha alpha dot, in Minkowski space. So take a point in Minkowski space. And then switch on the light cone whose vertex is at that point. So the light cone with apex at x, this will be defined by some function which fixes the retarded Bondi time in terms of x, r, lambda, and lambda bar. This is, I'm just writing schematically the equation for a light cone, if you like. And then, as r goes to infinity, this light cone will go out and it will intersect scribe plus. Right? And we call this intersection a cut. And this is defined by u is equal to limit r goes to infinity of this light cone function. And we'll call this g lambda and lambda bar. And it turns out it's a calculation. You can write down exactly what this thing is. In our coordinate system, this cut function is just x alpha alpha dot lambda alpha lambda bar alpha dot. Okay. So okay, points in Minkowski space correspond to cuts of scry with cut functions that look like that. Okay? The question is now, is there some kind of intrinsic way we can characterize cut functions that look like this? So this cut function is just the solution to a differential equation. Which is just two anti-holomorphic derivatives of G is equal to 0. The thing has to be a linear function of lambda bar. And I could also have written the complex conjugate equation, but I get that for free once I write this one because the thing's real valued, right? So cut functions that look like this are in one-to-one correspondence with solutions of this differential equation, okay? And it turns out that that differential equation is the same as the differential equation et bar squared acting on G is equal to 0. These are the same equation in our projective formalism. It's a fun exercise to convince yourself that this is true. And this equation has a geometric meaning. This is the condition that the cut U equals G of lambda bar of scribe plus is shear free. Or in other words, it was produced by a null GED congruence that was shear free. Okay? So this answers our question. Points in Minkowski spacetime correspond to shear free cuts of scry, and vice versa. If all I'm doing is standing out on scry, every time I walk around in one of these shear free cuts, I'm labeling a point in Minkowski space, and there's a 4-parameter family of those shear free cuts, which are just given by the coefficients, choice of coefficients in your solution here. Another way of saying this, if you like, is the kernel of et bar squared are the L equals 0 and L equal 1 spherical harmonics. There's 4 of them, right? And the choice of the coefficients in front of those 4 spherical harmonics is the choice of the vertex of the light cone that produced the shear free cut. Okay, so maybe a picture is helpful, maybe not. So here we are on scry plus, and I can consider generic cuts of scry plus, and then I can ask which of these cuts come from light cones that focus back to a point in Minkowski space, and the answer is kind of only these round ones, right? So it's always dangerous to use the colored chalk because maybe it won't erase, but these shear free ones are precisely the ones that focus back to points in space-time, okay? But now maybe, so okay, we've gone for an hour now and I haven't said the word twistor once. But now maybe this should start to ring a little bit of a bell, right? Because the correspondence between twistor space and Minkowski space was that a point in Minkowski space defined a sphere, a linearly holomorphically embedded Riemann sphere in twistor space, and something a bit like that is happening here. A point in Minkowski space defines a sphere that's embedded in a very particular way at scry. And in fact, this isn't a coincidence. This can be made precise, which is what we're going to do now.
But the difference is that it's only in one direction,
I don't know. A point on scry defines a null geodesic in Minkowski space. I'd say that's non-local in both directions. It defines a point on the conformal boundary, but not in Minkowski space.
If I take on scry this section should be section, I can construct point
I would have said, I mean, imagine in Twistor space. I take a curve in Twistor space, I can reconstruct a point. One of these lines in Twistor space, I reconstruct a point in space-time. That's a one-dimensional object going to a zero-dimensional object, and I would say it's the same here. Okay, so just an aside, everything here goes through for complexified Minkowski spacetime as well. So we focused on the Lorentzian real story here so that I can draw pictures like this and no one has a brain aneurysm. But the story, the mathematics of the story goes through, nothing changes with any of these equations if we consider E to be complex, right? So in this case, scry is the partial complexification you might call scry sub C, and this is C cross S2. So you can get all of complexified Minkowski space here just by complexifying the kind of Bondi time coordinate. You don't need to complexify the S2. You can complexify that as well. It doesn't matter, but okay, so I've told a story that was Lorentzian real, but secretly I've told you a story that was also a complex story. Okay. All right, so now for the last half hour, we'll actually do some Twistor theory. Okay, so recall that our definition of the Twistor space of complexified Minkowski space was all the z's in CP3 such that the lambda alphas were not simultaneously zero. And if the lambda alphas aren't simultaneously zero, and there's two of them, and they're defined up to overall projective rescaling, that means that in fact they're homogeneous coordinates on a Riemann sphere. So this means that the equivalence, projective equivalence class of these lambda alphas give homogeneous coordinates on CP1. So this means that there's a natural fibration, which we'll call pi, from PT to CP1, which just sends ZA, which is equal to mu alpha dot lambda alpha to lambda alpha. Right, and this defines a map to CP1 precisely because these lambda alpha are not allowed to all vanish simultaneously, which means they're good homogeneous coordinates on CP1. But turns out this Twistor space also comes with another projection. This projection was holomorphic. Right? So often you'll hear people say, oh, Twistor space admits a holomorphic fibration over CP1. That's fancy words for the existence of this map. But there's another projection that we can define which is not holomorphic, which sends, let's call this one P, and it's going to send mu alpha dot lambda alpha to square bracket mu lambda bar lambda alpha lambda bar alpha dot. Okay? So you hand me a point in Twistor space. It has this projective, this homogeneous coordinate. Z is equal to mu alpha lambda alpha. And I can define a complex number that's the SL2 inner product of mu with lambda bar and then I just take lambda and its complex conjugate. Okay? So who cares? Why is this an interesting thing to do? So under the projective rescaling, ZA goes to, let's call it B now, ZA on Twistor space, right? This is the projective scale we have built into the game for our homogeneous coordinates in Twistor space because we're on an open subset of CP3. We have that, well, lambda alpha does the obvious thing. Lambda bar alpha dot goes to B bar, lambda bar alpha dot. And what about this combination? Mu lambda bar, well, this goes to mod squared of B mu lambda bar. So that means that what this projection is doing is taking us from Twistor space to the total space of the line bundle O1, 1 over CP1. Okay? Here, lambda and lambda bar are the holomorphic and anti-holomorphic coordinates on the CP1 base. This contraction is now the fiber coordinate, right? The reason why it's O1, 1 is because you get B bar here when I do the projective rescaling. But this is the partial complexification of Scry, right? We just saw Scry with Lorentzian reality conditions was the total space of this line bundle where all the sections are real valued. Here, we don't have a reality condition on this contraction, so I've dropped the R, and that's this partial complexification of Scry that we wrote up there. Okay. So, there is a projection from Twistor space to Scry. For every point in Twistor space, I can get a point in the partial complexification of Scry. But what happens to the Twistor correspondence under this projection? Right, let's take one of our holomorphic, linearly embedded Riemann spheres in Twistor space. Let's put into this projection. What do I get when I project down to Scry? So what happens to the Twistor lines? So recall that each Twistor line is defined by those incidence relations we wrote down yesterday. So these were this linear equations, mu alpha dot was equal to x, alpha alpha dot lambda alpha. So under this projection from Twistor space to the partial complexification of Scry, what happens? Well, we just need to keep track of what happens to mu lambda bar restricted to a Twistor line. And well, what do we get? We just get x alpha alpha dot lambda alpha lambda bar alpha dot. And that's just, if you like, the cut function for the shear free null geodesic congruence that focuses back to the point x in space-time. So the picture one should have here, I should have drawn this further down, is that over here we have Twistor space with a Twistor line x, and under the projection P, this is getting sent precisely to the cut that the light cone whose apex is at x makes with scry. Okay? So this wasn't just some coincidence, it's really the same correspondence. You can think of the set of lines in Twistor space as the set of all these shear free cuts of scry. And this is, in its most elementary guise, the sense in which Twistor space is somehow holographic. Right? This Twistor correspondence is non-local, the way you expect a holographic correspondence to be. And in some sense, it's reconstructing the bulk of Minkowski space from this asymptotic data, these shear-free cuts of scry. But now the last thing I'd like to tell you all about is now what happens not just to the Twistor correspondence with lines and points in complexified Minkowski space, but this more powerful correspondence we talked about at the end of the lecture yesterday, this Penrose transform for solving zero rest mass equations. How does this behave under this correspondence? So consider a free massless scalar on M, which is asymptotically flat. And by asymptotically flat here, I mean compatible with this Bondi-Sachs expansion that we wrote down. What that means is that the conformally rescaled massless scalar, remember these things always have conformal weight -1. So my conformal factor was big R, so that's where the -1 is coming from here. I want this thing to go to some constant value at the conformal boundary of my, well, I want the thing to go to some nice smooth value on the conformal boundary of my conformally rescaled spacetime, and that's just saying that it should admit some series expansion k equals 0 to infinity phi k u lambda bar over r to the k. Okay, so the leading term here is r to the 0. That's because we're in the conformally rescaled metric. In the physical metric, the leading term would be 1 over r. So here, the kind of coefficients in this expansion, phi of k, these things take values in curly O minus k minus 1 minus k minus 1. For this whole thing to have the right conformal weights and spin weights, these coefficients have to take values in these bundles in our homogeneous formalism. That's another way of saying that the coefficients in a Peeling expansion are not actually functions. They're spin formally weighted functions on scry. Yes?
I'm slightly confused about that expansion. In the bulk, in the usual way, if we solve matrix equations, we know that they kind of also admit logarithmic columns.
Okay, I'm assuming smooth conformal compactification and peeling everywhere in sight here. Obviously, this is not a totally general assumption. Yeah. Well, sorry, maybe it's not obvious. This is not a totally general assumption, and logarithmic terms would spoil this. Yeah, we just don't require that it be a real section of these line bundles. Okay, so the fact that it's a scalar means that the entry here and the entry here have to be the same for all k, basically. So it has to be spin weight 0, right? Doesn't mean it, so if it's not spin weight 0, it can't be real valued. But, so this is a necessary condition for being real valued, but it could also be a complex scalar. Yeah. Okie doke, so the zero rest mass equation, which is just the massless wave equation for phi, what this does is it gives us an infinite tower of equations of motion at each order in R in this expansion, right? This is probably an exercise some of us have gone through before, figuring out what this is. This becomes a set of coupled equation of the form phi dot of k plus 1 is equal to minus 1 over 2 k plus 1, k to k plus 1 plus. Okay, so here, where dot is just the u derivative, okay, and this is the scalar Laplacian on the 2 sphere. Okay? And what you immediately see from this is that all of these coefficient functions for k greater than 1 are determined by the leading one, phi 0, which is valued in curly O minus 1, minus 1. Okay? And this, all we're seeing here is the statement what the radiative part of the field is. The coefficient of the leading 1 over R fall off is the thing we usually call the free radiative data of the field, right? And you see this explicitly. It determines up to functions of integration, things that are in the kernel of this differential operator on the sphere. It determines all the others. So the only one you get to choose freely is the leading one. Okay? So this is called the free radiative data. Yeah, they're functions of integration, but their U evolution is completely determined. Yeah, so these functions of integration you should think of as somehow corresponding to Coulombic modes of the field. So if they were constants of integration, they would be literally Coulombic modes, but they could have some angular dependence. Yeah, and just to keep the analogy in your head, if we were talking about a gravitational field, the role of this phi naught would be sigma naught, and the role of all the other things would be like the bonding mass aspect. Okay, so in fact, we can see this fact that this is the free radiative data, that it can uniquely determine the zero rest mass field extremely explicitly. Thanks to an awesome integral formula, which is not, I think it's fair to say, widely known, called the Kirchhoff-Datamar integral formula. So given some phi naught with values in O minus 1 minus 1, we can take one U derivative of this thing. So that's going to be weight minus 2, right? Because U is the fiber coordinate of O1, 1, so taking one U derivative knocks us down by 1 in both the holomorphic and anti-holomorphic weights. And then we can form phi dot 0 restricted to s squared of x. And what I mean by this is take this object, one U derivative of the free radiative data, and restrict it to the cut of scry corresponding to the point x in Minkowski space. So this just means we restrict it to u equals x alpha alpha dot lambda alpha lambda bar alpha dot. Okay, so that's what this symbol means. And then I can construct a scalar field phi of x by taking an integral over the shear free of scry corresponding to the position x times a weighted measure on the Riemann sphere times this data pulled back to the cut. Okay? So this integral is well defined. It's a 1, 1 form, and it's weightless, right? Weight plus 2 holomorphic, weight minus 2 holomorphic. Weight plus 2 anti-holomorphic, weight minus 2 anti-holomorphic. The gods are angry. Okay? So, so this integral is well defined. It gives you a scalar on spacetime, but also it's immediately obvious that the scalar obeys the wave equation. Okay? So how do we see this? So box phi now, I can bring the partial derivatives inside the integral using the shear free cut function, right? And this is just going to be d lambda bar, lambda alpha lambda bar alpha dot lambda alpha. And that's immediately equal to 0 because I'm getting lambdas contracted with lambdas, okay? So you can explicitly, I mean, I think this is an awesome formula because it's like sort of a kind of null version of bulk to boundary propagator sort of stuff you'd meet in ADS, right? So in ADS, what a bulk to boundary propagator does is it takes some boundary data on ADS and reconstructs the bulk field for you. And here what this is doing is it's taking radiative data on scry and reconstructing the linear bulk field for you. Okay? Yeah, please. Very good. So the integral assumes that the field is purely radiative. That is to say, all the functions of integration are set to 0.
So it's not really reconstruction, it's
It reconstructs the radiative free field from its bulk, from its boundary or characteristic data. Yeah, good. Okay. So you might now start thinking that this looks like another integral formula that we wrote down, namely the Penrose transform integral formula. And in fact, it doesn't look like it. It is the same thing. Okay? So now let's do the following thing. Let's consider the pullback of phi dot 0, right? So this characteristic, this radiative data was defined on scry or on its partial complexification. So is its u derivative. I can pull it back to Twistor space just along this projection P that we wrote down. So this is some object on Twistor space. It carries some anti-holomorphic weight on Twistor space, which is weird. We don't usually like writing down such things, but that's okay. We can get rid of that. We can consider d lambda bar p star, so pull back to Twistor space of this thing. And now this is a 0, 1 form on Twistor space that has holomorphic weight minus 2, right? Because this d lambda bar ate the anti-holomorphic scaling weight that we had in phi dot. Furthermore, d bar of this object is 0. Why? Because the only anti-holomorphic dependence that we can pick up when we pull back along this map, is lambda bar anti-holomorphic dependence. But we already have a d lambda bar here, and d lambda bar wedge d lambda bar is 0. Right? So that means that this object d lambda bar pullback of the once differentiated radiative data, this is actually an H01 PT. Curly of 2. And that's the cohomology group that is isomorphic to massless free solutions of the massless scalar wave equation on Minkowski space that we wrote down for the Penrose transform yesterday. So what this Kirchhoff-Hadamard integral formula actually is a gauge-fixed version of the Penrose transform, where you've demanded that your cohomology class, your representative of the cohomology class here, has this particular form. So for radiative free fields, you can always find a representative of the cohomology class of this form. And this is true for any spin. So gravitons, gluons, you name it. They all have Kirchhoff-Hadamard integral formulae that you can write down in terms of their characteristic initial, final data on Scri+. And those are all equivalent to the Penrose transform integral formulae that we wrote down yesterday, where the integral over the spherical cut then becomes an integral over this thing pulled back to the corresponding line in Twistor space. It's not surprising because the line in Twistor space and the cut on Scri are related by the projection from one to the other. Okay? So, yeah, before the gods get any angrier, I'll stop there for today.